Good morning, ladies and gentlemen. It is February 24th. Welcome back to another installment of ICP. Today we are moving on from our discussion yesterday on the history of the atom, and today we're going to be talking about elements and the periodic table. So I'm going to go ahead and share my screen. Okay, so today we are working, oops, is that the right one? Let's see. There we go. Okay, so now it's just sharing this. Okay, so like I said, today we're working on day 13, it's materials. So if you look on classwork, you'll see here we have the X ticket. Right below that is elements in the periodic table. This is where we're going to be working the PowerPoint guided notes. We have the practice, and this is a resource for you, periodic table that you guys are going to be using a lot. So I put this here, but I also want to tell you I did put it in the general resources. So if we scroll down here, there's now a periodic table. You can use this periodic table on any assignment, any quiz, or any test. Okay, so this is a tool for you to use. But without further ado, let's go ahead and get started. Let me go ahead and make sure I'm sharing the correct thing now. Share. Okay. All right, so we're going to start off today with a little quick review over the atom. So remember yesterday we talked about the history of the atom, all the different discoveries that different scientists made, how the atom changed over time. And what we can see here is a more current view of our understanding of the atom. So remember, there's two parts to an atom. There's the core, which we call the nucleus. And the nucleus consists of both protons and neutrons. So we're talking about this little dot right here in the middle, okay? Those green dots could be protons, the red dots could be neutrons, okay? If you're not in the nucleus, you're in the electron cloud, which is the space around the nucleus, okay? So again, here we have the electron cloud. So we look in this space, this is just a region where electrons are likely to be found. Likely to be found. Not guaranteed, but likely to be found. So remember, Rutherford told us that atoms are actually mostly empty space. Remember, he did that experiment with the gold foil, wherein he shot radiation at the gold foil. Most of it passed through and hit the film at the very back, but every once in a while it would bounce off. So the key is that if it was bouncing or being deflected, it's because it would come and it would hit the nucleus and bounce off or be deflected in a different direction. But most of the time it just passed through the electron cloud without any interference because atoms are mostly empty space and just kind of hit the back of the film. So in the nucleus, we have both protons and neutrons. Protons positive, neutrons neutral, pro positive, neutral, okay? And then we have electrons around the outside. And one key thing to understand is the number of electrons is always equal to the number of protons, which means the negative and positive parts are balanced to start off with. We're going to see that changes as atoms bond or join or combine. But the key here is when an atom is in its natural state, it has the same number of positive parts as it does negative parts. So the overall charge of the atom is neutral. Remember, atoms are extremely small. If a good way to think about the size of an atom, in 1 teaspoon of water, this is a teaspoon, not the big one, the little one. 1 teaspoon of water has 3 times as many atoms as the Atlantic has teaspoons of water. So if you literally took the entire Atlantic Ocean, and scoop by scoop, teaspoon by teaspoon, you counted each time you took a teaspoon of water away, you would have to do that 3 times in order to get to the number of atoms in just 1 teaspoon of water. So that shows you how incredibly small and how many atoms there are to make up the world that we live in. All right, this is a picture of Dmitry Mendeleev. He is one of the first people to put together something that we're going to focus a lot on called the periodic table of elements. Now, his periodic table did not look like the one that we're seeing behind his picture. He started off with just a number of elements. There were plenty of holes, things that we hadn't discovered yet, and there was a lot of missing information on there. But the amazing thing that Mendeleev did was he looked at the data of the atoms that they already knew. And he looked for patterns, he looked for trends. And what he saw was he started to see that as atoms got bigger in size, their mass increased, so he organized them by mass. And there are also some other properties we're going to take a look at today that also started falling into patterns. So the periodic table actually has a ton of patterns and a ton of information on it. And what we're going to be doing today is looking at how to decode that information, how to read that information, and how we can interpret that to use it to our benefit. So first off, how do you read the periodic table? Well, on the periodic table, everyone is a little bit different, but they always have the same basic information. Somewhere on there, you're going to have a whole number, and that whole number is the atomic number. So for carbon, in this case, the atomic number is 6. Okay. Somewhere on there, you will also have an abbreviation. That's the chemical symbol. So for carbon, it's just a capital C. Elements always start with a capital. If there's more than one letter, the second letter or second and third letters, if that's the case, will all be lowercase. This helps chemists when they're looking at a chemical formula, such as like C6H12O6, which is glucose. The C is going to be capitalized, the H is going to be capitalized, the O is going to be capitalized, signifying that those are 3 distinct elements. Okay, but if I looked at Cu, for example, if you find Cu, big C, little u, on your periodic table, you'll see that's copper. Okay, so each symbol starts with a capital letter, and that can help you determine how many atoms are in an element. Depending on the spacing of it, it might also include the element's name. So here we have carbon. Not all periodic tables have the names on them. The one hanging up in my classroom does not, but like I said, some of them do. And I think the one that I shared with you guys does have the name. And then you're going to see a number with a decimal. And that number with a decimal is the atomic weight or atomic mass. So this is just, a standard amount of each element. How much mass does it have? And we kind of categorize it that way. So we can compare the atomic weights of different elements. So how do I find out the number of protons, electrons, and neutrons an atom has? So remember, atoms are all made up of the same three main parts. They're all made up of protons, neutrons, and electrons. So the only thing that makes one atom different from another is the number of protons, neutrons, and electrons. So when we looked at carbon, we'll talk more about how I figured this out, but if I want to know how many protons carbon had, I would just look at its atomic number. So if I go back real quick, the atomic number of carbon is 6. This means it has 6 protons in its nucleus, in its core. If I want to know the number of electrons, I also look at the atomic number, because remember, when elements start off, they start off with equal number of protons and electrons. So that number is going to start off being the same. The only time I have to do some calculations in order to figure something out is to figure out how many neutrons there are. Remember, Chadwick was talking about the fact that the atomic mass of most elements is just double the number of protons. So that led him to the discovery of the neutron, the idea that there's another particle in there that has mass but doesn't have a charge because they weren't able to interact with it. So if you take away the number of protons, which is what you're doing, you're taking the atomic weight minus the atomic number, aka the number of protons, what you're left with is the number of neutrons. So let's go back and let's take a look at carbon. So carbon had an atomic number of 6 and it had an atomic weight of 12. We're going to round that to 12. You can't have 0.99 of a neutron. You either have a neutron or you don't. So we're just going to round this number to 12. If they ask you to report the atomic weight, though, don't round it. You only round it if you're calculating how many neutrons something has. That's key. So according to this, I would take the atomic weight, which is 12, minus the atomic number, AKA the number of protons. So I take 12 minus 6, and I find out that carbon, in addition to its 6 protons, also has 6 neutrons, because 12 minus 6 is 6. Okay, so again, number of protons, just look at the atomic number, record that. Number of electrons, look at the atomic number, record that. If you need to find the number of neutrons, you take the atomic mass, the atomic weight, minus atomic number, taking away the number of protons. Now, I told you that there were tons and tons of patterns on the periodic table. So let's get into what these patterns are and what they mean about the elements that are grouped together. So the periodic table can be looked at in 2 ways. It can be looked at as vertical columns, which we call groups. And we can also look at the horizontal rows, which we call periods. So groups have certain things in common and periods have certain things in common. But they're unique to each one. So let's take a look. If you looked at one atom of every element in a group, that's that vertical column, what we have here is beryllium, magnesium, calcium, strontium, barium, and radium. This is group number 2. Yep, group number 2. So if you look on your periodic table and you look at that second column, these are the elements there. If you looked at each one of these on an atomic level, you would see that they all have the same number of electrons in the outermost shell. Now, why is this important? Well, these are special electrons. The electrons on the outside of an atom are called valence electrons. And these are the electrons involved in determining how the atom is going to act. What is it going to bond with? What is it not going to bond with? How many bonds can it make? This is all determined by how many electrons it has in its outer shell. So when we're talking about people, you remember that old saying, don't judge a book by its cover, right? Well, that's not true of atoms. I don't care how many electrons it has on the inside because those are not active in the bonding process. I only care about how many electrons it has in the outer shell because that's going to determine how reactive or how not reactive it is. So for example, going back to our example of group number 2, we have beryllium and we have magnesium. If I look at beryllium, on the inside, beryllium has 2 electrons in the first shell, and on this outer shell, it also has 2 electrons. So these 2 electrons are involved in the bonding process. These inside ones are not. And then this black circle here, that's representing the nucleus, right? If we look at a different atom in the same group, like magnesium, I can see I've got 2 in the first shell, I've got 8 in the second shell, and I've got only 2 in the outer shell. Now look at that, 2 on the outer shell, 2 on the outer shell. So what that means about these 2 elements is even though they're different sizes, and even though they have different number of shells, right, orbits or whatever, this is like the Niels Bohr model, that's what we're looking at here. Even though they have different number of subatomic particles, number of electrons, the key is because they have the same number of valence electrons in the outer shell, they're gonna react in very similar and predictable ways, okay? We're gonna find out that every atom wants a certain number of valence electrons. So if they don't start with that, they're gonna trade, they're gonna steal, or they're gonna borrow, they're gonna do whatever they can so they meet this magical number. And the magical number I'm gonna tell you right now is 8. Everyone wants 8 electrons in its outer shell. That is the magic number. So valence electrons. That affects how the atom bonds. So the way the atom bonds is going to determine many of the properties of the element. Is it explosive? Is it boring? Is it inert? Is it going to change when it interacts with things like water? Or is it going to change when it interacts with things that are not polar, that don't have charges? All that is determined by how many electrons it has in the outer shell. So this is why elements in a group usually have similar properties. This is why sometimes groups are called families. It's called a family because, you know, members of a family sometimes have that certain characteristic, like, oh, that whole family, they talk so loud. Or, you know, that family, they walk so fast. They have similar characteristics. They have similar properties. This is true of every element in a group because they have the same number of valence electrons, those outer electrons. They're going to act in similar ways. They're going to bond. And similar ways. And that's really key. Now, that's the vertical groups or families. Now let's look at a period, okay, which is the horizontal row. If you look at every element in a period, they are not in any way going to react in the same way, but they still have something in common. Elements in a period have the same number of electron shells, not the same number of valence electrons. They have different numbers in their outer shell, but they all have the same number of shells, and that's really key. So let's take a look at an example. So here we are taking a look at period number 4. We've got potassium, calcium, scandium. I'm not going to go through that whole list, but then you end up with beryllium and krypton on the other end. All of these elements are very different and act very different. Here we have iron. Here we have nickel, copper, zinc, okay? Some of these you may have heard. These are very different. Iron and copper are very different from one another, right? Copper is that, brownish, orangish, metal. Iron has that darker color, but it rusts. So they act in different ways. They look different ways. They have different levels of conductivity, right? Copper is really good at conducting electricity. Iron is good, but not as good as copper. Iron's more brittle. Copper's more malleable, right? So these things are very important in determining the fact that all of these are going to act in very different ways, but even so, they have the same number of electron shells. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. Hey, wait a minute. The fourth period has 4 shells. Isn't that crazy? It's like the first period has 1 shell, and the second period has 2 shells, and the third period has, you guessed it, 3 shells. So the period number tells you how many electron shells that atom has. So even though potassium, iron, and krypton all act incredibly differently, they all have the same number of electron shells. So each group has distinct properties. The periodic table is divided into several groups based on the properties of the different atoms. So what we're going to do now, and if you look at your notes, you have some open sections here. Just take some of these notes. You don't need to write down everything, but I'm going to go through the major groups and how they act, so that we can see how different the atoms can be. The first group we're going to talk about is everything in group 1, and except hydrogen. Guys, hydrogen and helium are very, very different, so we have to kind of keep them in our mind a little bit different from the rest of the table, and I'll explain why later. But you see all the atoms here: lithium, sodium, potassium, rubidium, cesium, and francium. These are all alkali metals. So what characteristics do alkali metals have? Well, they're very soft, silvery colored metals. And the key here is that they are incredibly reactive. This means if they come into contact, if they're in their natural state, they come into contact with something like water or something like that, they can explode. So a lot of times we see ones in this group, they can be used in things like fireworks because they're very explosive. Not a lot of energy takes them, they will go off. Very, 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 very reactive. And that's important. The second group is called the alkaline earth metals. Okay, the alkaline earth metals are silvery white, and they're still pretty reactive. They're not as reactive as the first group, so they're not as dangerous, but they are still very reactive and can be explosive if given enough energy. Many are found in rocks in the Earth's crust. So if you're going, on a hike and you see a bunch of rocks on a rock face, chances are you'll find a lot of these elements in those rocks. Again, not as reactive, but still somewhat reactive, found in many rocks. So like magnesium and calcium, these can also be used in fireworks and things like that, because again, they are reactive, they're just not as reactive. Like potassium and sodium are very dangerous to have in the natural state by themselves because they're so explosive. Then we hit the giant chunk in the middle. We're not going to go through every row because not every row follows, a good set of examples. But The transition metals kind of mess with the rules a little bit that we're going to be looking at. Mostly when we're talking about rules, we're talking about the very top left side of this periodic table and the very right side of this periodic table. Things in the middle, there's still reasons to put them in rows and families, but they don't quite share exactly the same properties like the other groups do. So how can we talk about these generally? Well, number one, they're metals. So metals are good conductors of electricity. That means that electrical currents can pass through them easily. Most of them are also fairly malleable, which means they can be bent or hammered into wires or sheets. They're not brittle. They're not gonna break. So good conductors of electricity, and they're quite bendable. So we use them. We use transition metals in everyday life. So coins, tools, jewelry, car parts, planes, all of this, all transition metals. So they're very important to us. But there's not a good, easy way to talk about them in giant trends. Then you get into the middle of the table and you hit these things called metalloids. Metalloids are kind of like metals, kind of like not metals. They're kind of in between. So they share properties with both metals and non-metals. So some that we use a lot more, like silicon and germanium, are very important for us, especially in this day and age, because they play a big component in things like computers. Your cell phone, your smartwatch, your actual computer, your gaming console, your laptop, any of that has lots of silicon in it. And the reason for that is because it's a good semiconductor. It allows some electricity to pass through, but not too much. So again, computers, computer parts, Silicon Valley is where it gets this name from, that real tech industry, big complex in California. But semiconductors are very important, metalloids, kind of like metals, kind of like non-metals, and it makes sense they fall in between the two. Just past the metalloids, we get the non-metals, okay? Non-metals are just very, very different from actual metals. So where metals are malleable, it can be bent, non-metals do not bend very easily. They're brittle, they break. They're also not very good conductors of electricity. They don't allow electrons to pass through very easily. And that's important because, again, it makes them very different than the metals, okay? Unique properties. So we can see things like carbon, nitrogen, and oxygen. So these are a lot of the organic molecules for life, right? You need oxygen to breathe. You're a carbon-based life form. Nitrogen makes up 78% of our atmosphere. The air that we breathe is mostly nitrogen. Phosphorus and sulfur are also very important for the body and everything like that as well, okay, and for life. So non-metals. Then we get to group 17. Group 17 is a group called the halogens. Okay? Halogens, just like the lights, are a gas, and they are actually mostly poisonous. So we don't want to necessarily breathe these in, and they're fairly reactive as well. So they're quite dangerous, okay? Here's the key though. Let's take a look at sodium. Okay, here's sodium. I know it's grayed out, but you can kind of see it in the background. Here we have sodium. And here we have chlorine. Okay, oops, I can't see it because my menu's in the way. Move that. Here we have chlorine, okay, right here. This group 1 and group 17, are matches made in heaven. And we'll learn more about why, but these often react with each other, okay? So we can take sodium, an explosive metal, and we can take chlorine, a poisonous gas, and we can mix them together, all right? They actually like to go together. And it's a good thing that they like to go together because we enjoy this very much on our food. Sodium chloride is the scientific name for table salt. So you take an explosive metal and a poisonous gas, when they're bonded together, obviously table salt is as safe as can be. You don't have to worry about sodium being explosive anymore. You don't have to worry about chlorine being poisonous anymore because the properties are going to change when they bond together. That's pretty key. Just a little fun side note, a little history for you. Chlorine gas was actually used as a chemical weapon during World War I. So it was shot off in canisters, trench warfare, very nasty stuff. And then the gas masks back then were not very good. It was also used in Germany in World War II. So in the final solution, when Hitler decided he was going to exterminate the Jewish race, a lot of the gas chambers used chlorine gas. Chlorine gas irritates the lungs. Your lips are going to turn bright red, and your face is going to turn blue. Your face turns blue because it starts blocking you from getting oxygen, which is very bad. So you slowly suffocate and die by suffocation. What's really sad about chlorine gas is there were some people that thought that they had survived it, but later had realized that some of the gas had gotten in their lungs and caused other lung complications down the road. So chlorine gas, very, very nasty stuff. Don't accidentally make it. It's very bad. Now, why is chlorine so bad? Well, remember, I said you want to get to 8 electrons in the outer shell. And so how many does it have? It's got 1, 2, 3, 4, 5, 6, and 7. The only one it's missing is that last one. So this is looking to steal it from wherever it can. So this is why it's so close. It's so close to being happy, so close to having that 8 number. So that's why it's very, very reactive. The last group that we're going to talk about on the periodic table are the noble gases. The noble gases, kind of, you can infer by their name, are not very reactive. Think about the old days. Did the nobles interact with the common people? No, they just kind of did their own thing because they didn't have to worry about much. Noble gases are noble because they are not reactive. These are the most safe, secure gases in existence that we know of, because they already have, with one exception, they already have 8 electrons in their outer shell. Okay, the exception is helium. Helium is so small that that first shell can only hold 2. And so it has 2, and so it's first shell. So basically the outer shell of all of these are full. They're not looking for anything. They don't need anything from any other atoms. They are already stable. They are already inert. And they're, like I said, they're usually gases at room temperature. So because they're so stable, you can run electricity through them. If you ever have driven by a restaurant or seen a sign advertisement for a restaurant and they use that neon light, they are using noble gases to create that light. So what you can do with noble gases is you can run electricity through them. And when you do that, that excites the atoms. They start emitting light, they glow. And you can make some really cool stuff using that feature. So this is a little example of some artwork done by someone making lamps using the noble gases. So neon, the noble gas neon, like a neon sign, those were the first ones. When you heat that or send electricity to that, it turns the orangish red color. Argon will emit a pale kind of purplish lavender color. Helium will give you kind of a pale peachish color. Krypton is going to give you a silvery color, whitish color. And xenon is going to give you that deep blue color. So xenon, when you run electricity through it, is going to emit a deeper blue color. So again, this is just showing us the different ways that we can break up the table. We can either look at it as the families, the groups, those vertical, right? These vertical columns, these are going to all act similar. These are going to all act similar. These are going to, so remember they have similar number of electrons in their outer shell. They're going to act in similar ways. Or we can look at it in periods. And remember each period is just how many electron shells it has. So as you look through the periodic table, you'll notice there are 3 different types of elements. There are metals, nonmetals, and metalloids. Okay, we kind of went through that as we looked at the families. If you look at the entire left side of your periodic table, I believe yours is colored blue, and you'll see that that indicates that those elements are a metal. So metals are usually solid at room temperature. There is one example, if you can think about it, and that is mercury. Mercury is a metal that is liquid at room temperature. There's some others that are close to liquid at room temperature, but not quite. And if you look at the periodic table, the majority of elements are metals. Non-metals are in the upper right corner of the periodic table. So I believe it's like green or yellow. Can't quite remember off the top of my head on your periodic table, but it's a different color. And if you look in the upper right corner, those things like carbon, nitrogen, oxygen, phosphorus, sulfur, these are all the non-metals. And the key is that they are very different from metals. They're not conductors of electricity. They're not bendable. They're brittle. So they're just, again, very polar opposites. And then you get the stuff in between, the metalloids. Those are on the either side of the staircase, that diagonal line. And they really share properties a little bit like metals and a little bit like non-metals. Those are, remember, silicon and germanium. The semiconductors conduct some electricity, but not too much. That's important because your phone works on sending electricity from one place to another. So if it was like a really conductive metal, then that electricity would just go everywhere, not specifically where it's supposed to go. So the key is that the semiconductors allow you to guide the electricity to send the information where you want it to go and not spread out through the whole phone. Now, like I said, elements are trying to get to that magical number of 8 electrons in their outer shell. And if they don't start with 8, the only group that starts with 8 is the noble gases. If they don't start with 8, they're going to form either a compound or a molecule, or they're going to join and change in some way. So what is a compound? A compound is 2 or more elements in a fixed ratio. Okay. Once these atoms join together, the properties of the individual elements are going to disappear. It's going to create new properties of that new substance. So going back to our example of table salt. Table salt is sodium, Na, right? Sodium, that's in group 1, highly reactive explosive metal. Chlorine, which is a halogen, in group 17. Poisonous gas. These 2 bond together and become nice, boring, tasty table salt. Put it on my French fries, put it on my food. It's going to make it taste better. Okay. At no point do I have to worry about this salt being explosive. At no point do I have to worry about this salt being a poisonous gas, because once these bond together, they are changed. Okay, they are changed. They have new properties. Safe, boring table salt. So how is a compound different from a molecule? Well, a molecule is 2 or more atoms bonded together. They may be the same element or they may be different elements. So something can be both a molecule and a compound, but it can't. Sometimes there are things that are just compounds and not molecules. For example, here we have 2. This is on the left, we have water. So that's H2O, 2 hydrogens bonded to 1 oxygen. And over here, we have what's getting me through today and probably you as well. This is our wonderful caffeine molecule. And what we can see here is caffeine has 8 carbons, 10 hydrogens, 4 nitrogens, and 2 oxygens. And if we look through here, we can kind of figure that out. Obviously, the 2 red ones are oxygens. The 4 blue ones are the nitrogens. The 8 black ones are the carbons. And the 10 white dots are the hydrogens. Again, each of these has different properties, but when they join together, it makes the magic happen. So when it's 2 of the same element, we call it a diatomic model, di meaning 2. So for example, a diatomic model is oxygen, right? The gas that we breathe to stay alive. It's not single oxygens. You don't take in single oxygens, you take them in pairs. So there are 2 oxygens bonded together. This is also true for nitrogen gas. The majority of the gas in our atmosphere is nitrogen. Remember, about 78% of the air that we breathe is nitrogen. Only 21% of it's oxygen. Hydrogen gas is another one that forms with bonds with itself. And we'll see why once we get into the bonding types about why these can form bonds with themselves. All right, sometimes you have elements that have a slightly different mass number. And this is because they have slightly different number of neutrons. And when that happens, we call it an isotope. So naturally, we don't fully understand why. Naturally, sometimes elements have 1 fewer or 1 extra neutron, and it makes it less stable. When it doesn't have the correct number, it means it might break down at some point. It's not going to stick together as well. So isotopes are what we call these. So if we took a look at boron, we got boron 10 and boron 11. If you look at boron on the periodic table, find B, it's number 5, you'll see that that means it should have 5 protons. And if you look at the mass number, it's 10.8. Why is it 10.8? Why is it a decimal? Well, it's because of those isotopes. Sometimes you find boron with 5 neutrons. Sometimes, for some reason, you find boron with 6 neutrons. And you can see that if you were to do the math. Boron has a mass of 10.811. If I take 5 away from 10.8, I end up with 5.8. So again, we would normally round that up, but in reality, the reasoning for that is because there are a lot of isotopes of boron. Some have 5 neutrons, some have 6. Now, what are isotopes and how can we use them? Well, when they break down, they're going to release energy. And so we can actually use that to our advantage. If you have ever had a bone scan, what happens is they inject you before with this isotope into your bloodstream. Now, blood is going to flow to where you have any broken bones. So if like, for example, when I was in college playing basketball, I had multiple stress fractures in my foot. They couldn't see it with an x-ray because your ankle has lots of bones in it. It's a very hard place to x-ray. So instead what they did was they gave me a bone scan. They injected me with the isotope. We waited for a while the isotope circulated in my body. And then what happens is while the isotope is in the blood, every once in a while, because it's not stable, it breaks apart. And when it breaks apart, it releases a little bit of energy. So they take a sensor and they put the sensor on the area they want to look at, and they look for these little pings, these little light ups of energy as these isotopes naturally break down. And if you see a lot of these happening in the same area, it means that the blood is trying to repair something like a break, like I had in my ankle, and that can tell you that your bone is in fact broken. Okay, so we use this a lot in medicine. All right. So those are the notes about the periodic table. Again, remember, it's organized in very, very intentional ways. The vertical columns, families share similar properties, same number of valence electrons. The horizontal rows, the only thing they have in common is the same number of electron shells. So the structure of the atom is something we're going to start to focus a lot on, especially going into tomorrow's lesson. We're going to go back to Niels Bohr and take a look at his model and take a look at a couple different atoms. So what you have left now is the practice, okay? If I go ahead and share that screen, okay? Here's the practice for you. At the very top, just a little review of the atom. Tell me what charge it has, if it has one, and then where I can find it in the atom. And then, I don't know why this is, in any case, I don't know why that's got FL. That must be a formatting thing. Anyway, this is just a little review of what we talked about, okay? Where do I find things? Where do I find that information? Then what you're going to do is you're going to take a look at the first 10 elements and compare them. So you're going to write the name first. You're going to write their atomic masses. You're going to see how many protons they have, how many electrons they have, and you're going to calculate. Remember, you have to calculate, you have to do the math here. Atomic mass minus number of protons. This is why I put these two in this order. Take this number minus this number. It's going to give you the number of neutrons. So you'll see how many neutrons it has, and this way you'll be able to get a good comparison of the first ones. This I want you're not going to be able to do on the computer, so we're going to actually hold off on this until I see you guys again on Monday. So don't worry about the second page now. You can't make these drawings. It's a nightmare to try and do in here. So this will be what we start off with tomorrow, just diagramming some atoms. Or not tomorrow, excuse me. Well, tomorrow we do have class, so we'll be looking at the atomic structure. So we'll do this half of this on Monday. Hooray for distance learning. After you guys get done that, go ahead and submit that in. The only thing that you do have left after that is the X ticket. Go ahead and open up that form, fill in your answers, and submit it. If you guys have any questions, again, don't hesitate to reach out, nick.welsh@excelcenter.org or on Facebook, Tech Nick Welsh. All right, guys, hope you have a good one. I will see you on the Zoom tomorrow.